ahead and resume the recording. So yeah, the main thing I just said before I resumed the recording was if you're have done the extra credit but had trouble submitting on a Moodle, get it into me. Some people had asked for extensions, but I've only gotten one so far. So all right, so we'll finish up on the OFDM type stuff, and then we will work on 5G. But actually, let me first talk about the test. I uploaded this this morning. It's not a complete preview yet. It's still basically saying that you're responsible for everything that we've done in the course. The final exam is comprehensive. And but I've kind of jotted down just some things that I expect you to be able to handle. You can go back and look at previous exams to get an understanding of what I'll probably be asking for on the final exam. And then things like, okay, so I'll talk just a little bit more about MIMO here as we look at how MIMO's implemented in 5G. And in particular, I'll talk about this Alamuti approach, which is kind of a classic type of approach. So anyway, I'll talk about that a little bit more. But yeah, understanding that MIMO benefits from multipath channels with significant delay spread. If you just got a line of sight and no reflections, MIMO's not going to do a whole lot for you. We can do a linear combining at the receiver, but if we can also do pre-coding at the transmitter, but that requires us to be able to send channel state information somehow to the transmitter. And then we talked about OFDM, orthogonal frequency division multiplexing, and there the key is we're trying to squeeze these frequencies channels as close to each other as possible using this principle of orthogonality. As it turns out, we can easily process this using inverse discrete Fourier transforms or fast Fourier transform as an algorithm at the transmitter and discrete Fourier transform at the receiver. And we'll talk a little bit more about that. Did not finish that lecture last Tuesday. So, and I'll talk about 5G and cellular networks today and probably spill into Tuesday. But I'd like you to understand the three use cases I put out there and the key drivers of some of the requirements in 5G. You know, maybe I'll ask you to name two or describe two out of the ones I list or something like that. I don't know. So, and then we'll talk a little bit today about how in cellular networks, we're kind of dividing up the spatial dimension and actually using lower power, shorter range communications to be able to reuse the spatial dimension. There's a concept of frequency reuse we'll talk about, handing off from one cell site to another, and then talk a little bit about the split RAN concept, which is a newer idea where we're doing some of the processing of that radio waveform and supporting layers of that network stack in a cloud, well, typically an edge type cloud environment. So you might have an edge server and it's responsible for doing kind of the high level radio access network processing for a number of different base stations. And then they would be connected via fiber out to the radio heads that are actually doing the transmitting and do all that in a time sensitive, time constrained way. So I'll talk about that a little bit more. And then On Tuesday, we'll talk a little bit about standards, the process, develop standards, how they promote compatibility. Typically, the transmission is waveform is specified, and much of the receiver implementation is left to the innovation of the various companies that are developing radios. But the transmitter, by specifying it, we know what that waveform is going to be on the air when we receive it at a receiver. So and that's compatible. I just listed a couple of standards organizations. 3GPP is the one that really handles our mobile communications, LTE, 5Gs, whatnot. IEEE does a lot with Wi-Fi and personal area networks and things like that, and then Bluetooth, and there's a bunch more, but those are probably the biggest at the consumer level. And then briefly talk about some research trends on Tuesday or maybe next Friday. Next Friday will be a semester review. So and I will try to give you a little bit more guidance on the final exam by that time. The final exam is May 5th, I believe. So but it's written on that exam preview that's up on Moodle. All right, so trying to move quickly today. So on Tuesday, we talked about OFDM, orthogonal frequency division multiplexing. This is the waveform that was used in 4G. It's being used in 5G. It will likely be used in 6G. It's used in a number of versions of Wi-Fi, all the later versions of Wi-Fi. It's also used in a bunch of different digital television standards, both here in the US and in Europe, and a bunch of different areas. So it has it's quite sophisticated, ties together a lot of different things, but it is advantageous, very advantageous in the type of communications that we're dealing with these days, and wireless communications. So we see it all over the place. So we talked about how, as it turns out, that this equation here, when we look at these symbols that we're trying to send with orthogonal spacing, that looks like a Fourier transform, discrete Fourier transform, where K is our frequency term. And this 1 over T is kind of our fundamental frequency. And so this is actually the inverse discrete Fourier transform. So we're going from kind of a frequency domain representation to a time domain representation. So so we can do that by taking in a whole host of different subcarriers, and then doing an inverse Fourier transform on these. And then if we have NFFT coming in, we have NFFT coming out, right? But this over here, this would be kind of a frequency domain representation of the signal. This would be a time domain representation of the signal. These are all coming out in parallel. We have in this model, simplistic model, not looking at MIMO, we have one channel. So we need to take all these. There might be 1,024 of these, or 4096 or something like that, right? And we need to take all those being processed in parallel and convert those to serial. So we just order, sample these in order and kind of keep running around this cycle here. Then we send that over the channel, and then do the inverse response over here. Now, each of these different subcarriers are now modulated using some level of, for example, QAM, MRE QAM. And what we can do is, if this spread of subcarriers, and again, I've drawn 8 here, but it's more likely 1,000 or so, and this might cover 10 megahertz, 20 or 50 megahertz of spectrum when you add it all up. and the channel may vary in response over this due to fading, right? So we might have at, let's say, lower frequencies, we might have low loss in our channel, and therefore we'd have a high signal to noise ratio, and in other parts we might have some shadowing or some fading, and we would have a low SNR when we have because we our signal is being attenuated, right? And when we have a high SNR, we might use something like 64 QAM. But where we have a low SNR, we might have something like QPSK or just BPSK, right? So something that has much greater distance between the symbols. Remember that concept from before the midterm. So if there's greater distance between the symbols, and we have better noise immunity. So this way, we kind of fill up all of these different carriers with the best bandwidth efficient modulation scheme that we can at these different channels. And it's a process we call water filling, because it's kind of like if you looked at this as like let's say the floor of a pond or something like that, where sometimes it's deep and sometimes it's shallow, and you're going to fill that pond up with water. That water is going to reach an equal level, but there will be different depths here at different SNRs. So if you see that water filling term, that's what it's referring to. So we can do that, and we can get the very best bandwidth efficient modulation that the signal noise of each of these channels will support, instead of having to like look at the overall bandwidth and looking at the worst case. We can kind of optimize it on a subcarrier basis. So all right, so now there's an issue here, and let's look at this blue line here. So this is a cosine signal here, right? Starts at 1 and then travels down here to, I guess, about 5, and then it's modulated, right? So this looks like a BPSK type signal, or binary antipodal type of signaling, right? And so at this time instance, I'm going to flip the modulation, because now I've got a symbol coming in at that's supposed to be a minus instead of a plus, right? So then we have this kind of instantaneous or near instantaneous switch in phase, and then we've got another few cycles filling up that symbol, right? So now let's consider that there's a reflection in our environment, and we've got another signal path that arrives at the receiver at a slight delay. Okay, so what happens there? Well, yeah, I drew it at the same amplitude. Might be diminished a little bit, but could be pretty strong, right? But there's a delay to it, and we see over here that there's some issues right here at this interface. How does a receiver work, right? So that receiver is going to integrate, whether it's in an integrator or in a match filter. It's going to process from 0 to T, or let's say NT minus 1, N minus 1T to NT, right? So, somewhere in this process, it's integrating over this interval T, and then it's going to sample at this point and make some decisions. But what's happening here? There's some misalignment, right? And so we're not going to get this energy contribution, but we're going to get this weird energy contribution over here, right? So we're missing some energy from the reflected signal, and we have some energy from the previous symbol. So that's kind of messed up, right? So what can we do about that? Well, let's transmit a longer symbol, longer than this just strictly N or T, right? 0 to T. Let's add a little bit, but we're going to add it at the beginning. Okay, we're going to call this a cyclic prefix. The prefix comes from the fact that we're putting it at the beginning, and but now we're still going to just integrate over this OFDM symbol time frame. So now we've got a little where these transitions occur. We're going to build in a little bit of a gap, and we're not going to look at that data, right? And instead, we're going to kind of focus still on this region of the original symbol. Now, what do we put here? Well, we don't put zeros. Let's put a copy of what's over here at the end of the symbol up in the front, right? So what does that mean? Well, we've got to form up this symbol first, right? And that's going to produce it's going to be produced via this IFFT, inverse Fourier transform. And we're going to go through this parallel to serial conversion, right? So we're going to be right here at this output of the parallel serial converter. And we're going to take what's here and stick it in the front. And so we would take this type of signal and stick it over here, right? So that's going to kind of smooth this out and what we're going to end up doing is we're going to throw away that cyclic prefix. The part of the symbol that the RX processes now has all the correct signals, even in the delayed path, okay? And that's going to lead to easier equalization of the received symbol. So we're not going to have to try to equalize all this out. I know we didn't talk about equalizers in this course. We really didn't have time. That's a challenging type of thing to compensate for in your receiver. So let's do this. And there's an expense of wasting time and energy transmitting the cyclic prefix, right? We're not going to use it. So we're like taking up time when we could be sending actual data. And it's causing us electrical energy to send it. So there's a cost of doing it, but it's overcome by cleaning up that signal and having a better result when we're focusing on this. And again, that's because of this discontinuity. I wish we spend more time on this because this was a bit of a challenging concept when I started learning about OFDM concepts years ago. Me and some guys actually ended up using that to get a patent and do some really cool things about combining carriers using that cyclic prefix. But yeah, it took me a while to understand. So, but yeah, hopefully you can kind of understand that concept and that's what I'd look for, is that there is this discontinuity. That's okay, except that it's offset in time. And so we're going to kind of take a copy from this end of the frame and stick it up here, or into this symbol. Sorry, frame's not a good choice of words here. Into this OFDM symbol and paste it up front here so that we kind of smooth this this out there.
Professor?
Yeah.
To go back to the slide with the signals. So I understand that two signals are, time delayed, but why does this continue to happen? Like what causes like that signal to drop to a null for the two at that like 5 second time?
Oh, so why is it changing? Why
Yeah.
do we have this change here?
Right.
That's part of the modulation. So in this case, we assume that it was going to be a BPSK modulation. And so we have these two different symbols, right? And this would be a plus and this would be a minus. But those symbols are composed of these 5 periods of cosine waves. I guess I did kind of skip over this little subtle point here that might help you to understand it, or understand the problem. If you look at these two waveforms, right? These two signals in the receiver, they're going to combine via superposition, right? Assuming that things are fairly linear, right? And so if we call one this A1 times cosine omega t, but the reflected one is this A2 times cosine omega t plus theta, right? Where that theta is representing this little bit of delay in the transmission, right? So this is what the receiver sees, this A times cosine omega t plus phi, right? Well, I'm just using different coefficients and different variables here. But it's the form of this that I think is important, is that if you take these two cosines and you add them together, you get another cosine with a little bit different amplitude and a little different phase. So if we see this is what we transmit, this is what we're receiving, right? Because of this reflection. Well, we're already rotating as we propagate along as that wave propagates, and we already have some attenuation. So our receiver already needs to compensate or equalize for phi and A. And so if we didn't have these discontinuities, this summation of these two waveforms would still look like a nice cosine wave that we could equalize and maybe draw a threshold here and say, okay, that's one symbol, that's the other symbol, and we can detect that, right? But this discontinuity kind of messes this situation up here a little bit. So again, what we're going to do is we're going to take the last part of this and kind of paste it up front here to kind of smooth things out. And then so this will kind of eliminate that discontinuity, and then we'll look from here to there. This cyclic prefix will end up kind of providing that the desired characteristic of that reflected symbol there. Okay, so the reflected ray. Okay, and then so ideally all these subcarriers linearly combine. So the Fourier transform, if you peel it apart, it's a linear transformation, right? And so all these subcarriers end up forming this flat top spectrum, and but we typically use guard zones at the edges of the spectrum to fill with subcarriers, because in real life there's going to be another I'm sorry, I'm drawing on my wrong screen here with my mouse. So this is all the different subcarriers, and then at the edges we would use a guard band and just fill those with zero subcarriers. So we might be using a 1024 point FFT, but maybe we're only filling 600 or 800 of those carriers with actual data. And we we fill kind of the edges of the band with 0 values, right? So, and that helps because, as I was starting to say, we're going to have another channel right next to this one, another one right next to that one, and we want to kind of minimize any interference because of some non-ideal linearities in our system, non-linearities, or some inadequate filtering and stuff. But this is nice because in a in a linear system, you have kind of a natural frequency boundary to these waveforms. So it's kind of self-filtering in that respect. All right, so real quick, some benefits, some pros. It's flexible to M-ary modulate each subcarrier depending upon the measured signal noise ratio in that small section of spectrum. And we kind of optimally fit to the fading over the whole band, right? So as I was saying near the beginning of the lecture, if some areas have poor SNR, then we'd use something like a low M ary type modulation like BPSK or QPSK. But if we're having great signal noise ratio, then we can use something more like 64 QAM or even 256 QAM. So the IFFT process spreads each input symbol in time. This is an important concept that may not jump out at you right away, but if you think about it, when we move from time domain to frequency domain and vice versa in these Fourier transform processes, we're trading off resolution. So if you're looking at a frequency domain signal, in a frequency domain, we have lots of frequency resolution, but we don't know what's happening time-wise, right? And the same thing, if we're looking at a time domain signal, we can see what's happening in time, but it's hard to pick out what's happening in frequency, right? So that Fourier transform process, we're kind of trading off either great time resolution or frequency resolution. So similar concept is happening here, is that each symbol, if we were just sending out each of those QAM symbols out over the channel without doing this whole OFDM process, then we would be having to send them really fast, and therefore we might have some intersymbol interference issues and multipath effects, which also lead to intersymbol interference and all. So there's going to be a limit on how fast we can send those symbols. Well, in this IFFT process, we're going to kind of spread this symbol out instead of having to send this symbol, then this symbol, then this symbol, then this symbol, so on. We're sending it in parallel, basically. We're sending all these in parallel. And so instead of going at the subcarrier rate, we're going at the OFDM symbol rate, right? So where the OFDM symbol here is a combination of all those 1024 subcarriers or whatever, right? So we're in a sense dividing this symbol rate by on the order of 1,000 or so. And that means that we're basically stretching out the time that these subcarriers are on the channel. Now they're all smushed together in this process and parallelized, but done in an orthogonal way so that we can recover them. But the the rate of change of the stuff on this channel here is a small fraction of the rate of change that we would have to otherwise. So that helps us with things like ISI and all, okay, because we're basically stacking these things in frequency and sending them all in parallel. Can allocate different users to a subset of subcarriers over a number of OFDM symbols. So if you have these, 600 or 1,000 or 2,000 subcarriers, I can give user one 20 of those subcarriers, and I can give user two 10 of those subcarriers, and user three 40 of those subcarriers until I've allocated up all of that time. And also so I have some flexible scheduling that I can do to be able to support multiple users at the same time. I think I've got a chart in the 5G section that might explain that a little bit. All right, so there are some challenges, right? So we haven't talked a whole lot about Doppler in this course, but it does exist. I think I probably mentioned in these LEO satellite type constellations, the Doppler effects are quite large, as that satellite rises above the horizon and then tracks above you and then sets above the below the far horizon. That pass at low Earth orbit takes about 15 minutes, 10 to 15 minutes. So you're traveling a long ways in that time, and you're going to see a huge Doppler shift. But we also see this in mobile communications and that type of thing. So if you have a big Doppler shift, then these at the receiver, the signals are going to be maybe shifted here. Instead of lying in this maybe 15 kilohertz, pretty narrow subcarrier, maybe I've got 2-3 kilohertz worth of Doppler shift, and the whole spectrum slides in this area. So I've got to figure out how to compensate for that, or I'm going to have part of the signal that was supposed to be in subcarrier one bleeding into subcarrier two, and on down the way, and that's going to make it really hard to separate out those signals. We basically lose our orthogonality when that happens. Same type of thing happens in the local oscillator at the receiver when we are trying to down convert this from, let's say, 2.5 gigahertz down to something that our analog to digital converter can process, maybe 100 megahertz or something like that, right? And if I've got a lot of noise on that oscillator, then that's going to likewise cause some problems in this alignment of these very narrowband subcarriers. So narrowband subcarriers has some advantages, but they are susceptible to these frequency shifts. When combining many modulated carriers, when we look at this, there's 1,000, 2,000, maybe 4,000 subcarriers that are combining into this composite signal, right, through this IFFT process. And each one is modulated with different data, and some are modulated at 64 Comm, and some are modulated at BPSK or QPSK, right? So as it turns out, all these are going to kind of add or subtract. They're going to constructively or destructively add according to their amplitudes and phases. And as we combine, this is going to cause through the central limit theorem, regardless of the distribution you have on any given carrier, if you've got a whole bunch of these, then you're going to have a distribution that looks Gaussian. via the central limit theorem. And that means that we do not have constant output power. Our output power, if it's nominally, 10 watts, then we might have situations where a peak, kind of a worst case combining kind of instantaneous, but a worst case combination could be 13 times that, on the order of 13 times. That's an approximation there, but 13 times is basically 13 dB is 20 times, right? 10 dB plus 3 dB. So it's a factor of 10 and then double it from that 3 dB. So it's 20 times the baseline. So if it's 10 watts to begin with, then our peak is going to be at 200 watts, right? So your power amplifier is going to be called upon to amplify up to 200 watts, even just for a moment, right? Well, it's probably not going to be able to do that very easily, right? And we could spend an hour talking about that, or a whole course on that actually. But that makes your power amplifier design very challenging. So it's very hard to amplify linearly and efficiently. So that leads to a lot of money in your power amplifiers. It's big on the base station, but it also has an impact on your handset, because your handset's not putting out 10 watts, it's putting out maybe 100 milliwatts or something like that. But now your power amplifier, instead of being several inches on a side, is on a chip, a little tiny chip, right? And so heat dissipation and all those same issues are hard in that power amplification. So that's probably one of the biggest challenges with OFDM. This is